All right. Hello, everyone. Thanks for joining our Sodick and Friends webinar series. We're happy to have you all. We got a good crowd today, and we got a great speaker, Umberto Catignani, with Orbital Plastics Consulting. I'm going to start off by introducing myself. For those of you who don't know, my name is John McNamara. I've been with PlusTech now for a little over 3 years. I cover Minnesota and parts of Illinois and New England area. Um, and I'm really enjoying working with this team we have here. And that brings me to our national sales manager, Len Hampton. I'll let him introduce himself for those of you who don't know, which is probably not many. So go ahead.
Thanks, John. Appreciate it. Yeah, it looks like a near record, definitely in the top three record crowds we've had. We've started this back in 2020 in the height of COVID. We've got probably over 50 of these webinars in the books already. So yeah, I've been here 20 years. Actually, Dale Jackman, raise your hand, is is a new technical sales and has some 5 or 6 key territories as well. I'll let him explain that too. But we brought him on just last week, coming from the plastic industry, but more from Gardner Communications from the media side. So many of you probably already know him already too. So we're very happy Dale joined us, and look forward to many years of success with Dale and his territories. Bennett or Dale, sorry, maybe you can introduce yourself.
Absolutely, and thank you for the warm welcome, Len. I did see a few names that I'm familiar with on the attendee list, so I'm looking forward to meeting the rest of you. But as Len mentioned, I was previously to my time with Sodick, with Plastics Technology Media brand, where I helped run that publication, as well as before that, I was an extruder myself. I was a production manager. So I've got some time turning pellets into parts myself, but looking forward to learning this side of the business as we move forward and partnering with all of you.
Thank you, Dale. John?
Yeah, we can go down the line here. I'll start with Bryce.
Hello, everyone. Bryce Masco, been with Sodick Plus Tech now almost 2 years. I cover Illinois, Indiana, New York, Ohio, Pennsylvania. Excited to see what Umberto has for us today.
Thanks, Bryce. Bennett?
Yeah, thanks, guys. Bennett Howard, been with Plus Tech 8 years, and I cover mainly the Southwest, kind of Southern California, Arizona, Colorado, Utah, some medical hotspots out there, and West Michigan and Milwaukee for kind of local territories to us. So, hey, Umberto, good to see you, buddy.
Hey, good to see you.
And then, yeah, thank you, Bennett. And then last but not least, Kohei.
Yes, thanks for joining all the time. We like to introduce many of our technical partner, like Umberto. We like to make a network hub for those who want the precision molding area. And we're going to be the trade show soon, MDM West and PT Expo. Please, let's meet there if you're there. I have exciting news that we're going to open Europe operations in this year. So those who have some reach to the Europe, please reach us. Like to start working with you guys as well. But yeah, looking forward to work this year with everybody, and hope you enjoy this webinar series. Thank you.
Thanks, Kohei. Before I move on to introduce Umberto, I want to go over a little bit about how this is going to work. Obviously, Umberto will give his presentation for about 45 minutes, and then we'll do a Q&A portion at the end. So please, throughout the presentation, submit your questions on the Q&A tab you'll see at the top of your screen. Don't submit them to the chat function. We won't be looking at that. We'll only be looking at the Q&A portion. So submit your questions there, and we'll get to them at the end. And then, without further ado, I'll introduce Umberto. He is the president of Orbital Plastics Consulting. They're a consulting firm with more than 150 years of combined experience, and they have an expertise in scientific molding, training, material selection, part and mold design, in-mold instrumentation, project management, and equipment selection. Umberto is also the past president of the southern section of SPE and has more than 30 years of hands-on experience. He's certified and trained hundreds of plastics professionals, and he has worked for IBM, General Motors, Delphi Automotive, and Husky Injection Molding Systems, and has a master's degree in polymer engineering from the University of Akron and a bachelor's in materials engineering from the University of Cincinnati. So I will let Umberto take it away.
Thanks, guys. I appreciate the introduction. I appreciate the opportunity to speak today. It's always a pleasure to do that and be on calls with you guys or this presentation. So with that, I'm going to go ahead and get started. But basically, we're going to talk about the relative viscosity curve and also velocity capability studies to and cavity imbalances to establish optimum plastic flow rates. I get asked all the time, what injection speed should we use? What's the optimum injection speed? And inevitably, it's a hard question to answer. It depends on cosmetics. It depends on capability of machines. There's a lot of factors. But real quick, scientific injection molding, you guys all know we've got the 4 primary plastic conditions which dictate our process. And we want to establish these when we're debugging a mold, setting up a mold in a machine. And that allows us to, move molds from one machine to another. I just touch on this quickly because, as processors, we have the ability to, change a lot on the machine settings. And, that's going to be based on what does our customer, require. Obviously, if we're making bad parts, that's our signal to go to the machine and change something, right? But ultimately, we do have these 4 primary plastic conditions, whether used are documenting them or not, but they exist, and this is a great way to help move molds from one machine to another and duplicate that process. And part of this talk is doing that, focusing on plastic flow rate. So I throw this slide up because I think everybody in industry understands this, that, I can't just load the process up every day from the machine and make the exact same parts. There's always going to be variations, lot to lot variations in material, dryness. But I'm sure you guys have heard many times, we were making good parts yesterday. Why aren't we making good parts today? Second shift, third shift, on and on. But this is, I think, an important slide that I always try to show to people that might be new to injection molding or not on the floor doing some, technical molding, things like that. But so again, moving molds from one machine to another is what we're trying to do, smaller machine to a bigger machine. If I can make parts on this smaller Sodick, then I should be able to make parts on another machine if I duplicate these 4 primary plastic conditions. So with that, let's focus on plastic flow rate, or if you want to think of it as the volumetric flow rate. So we know that as we fill faster, increase our plastic flow rate, the amount of molecular orientation, we have a velocity profile. We have drag flow at the wall. We eventually get plug flow when the plastic starts to skin up, and then we have fountain flow here. So, that flow speed differences generates this orientation. That orientation thereby lowers the viscosity of the material, non-Newtonian flow, and then shear heat. Obviously, when these chains are flowing at different speeds, they'll be rubbing against each other, generating friction. So flow rate's very important. If I change injection speed, I change the heat generated. So I'm actually changing, go back to the 4 conditions, I'm actually changing the cooling rate. I could be changing the crystallinity, shrinkage, the amount of flow rate. Fill faster, I put in more molecular orientation. How fast do I cool is retained orientation. So these are all linked together, but I thought I would just touch on that. And just showing an apparent viscosity versus shear rate curve for several materials out here I just picked. And obviously, viscosity is decreasing as shear rate's increasing. That should be no surprise to anyone here on this. But let's talk about the machine rheology curve that's used out there quite frequently. So, fundamentally, the equation is, we're going to take the fill time and multiply by the hydraulic pressure and convert it to plastic pressure using the intensification ratio. And then we're going to use our shear rate as 1 over the fill time. So, when I first came across this, I learned it, but I struggled with it because it's not a real viscosity, relative viscosity. And also this equation here is really just calculating the area under the curve, in the green box. So you're really calculating a rectangle, not even the area under the curve. But then still, it's not a viscosity. And then 1 over fill time, shear rate, as I shown in the previous slide, we're in 10,000 reciprocal seconds here. So just 1 over fill time is not truly a shear rate. So with that, I just thought I'd show up, like Autodesk uses the cross WLF viscosity model. So you can see this viscosity equation. You can see, I'm not going to go through this, but this is, this is the zero shear viscosity here. And this equation will drive that variable here. And, this is done with the apparent viscosity data that you would generate from a melt rheometer, and you have to do a lot of fitting to get these constants here. And we even have the glass transition temperature here. So actual apparent viscosity or viscosity you would use to do mold filling analysis is completely different. It's not a relative viscosity, it's an apparent viscosity. So let's compare the two and go from there. So if I do a relative viscosity curve, what we do is we want to pick a range of injection speeds, machine velocities, and we want to plot them as relative or effective viscosity versus shear rate. And as I said here, this viscosity is going to be the intensification ratio times the hydraulic pressure. So just back here, and the fill time, shear rate will be 1 over the fill time here. So if we do this kind of math, and I have this data, what typically people do is we will use the shape of this curve to determine an optimum injection speed. So if I do this, then we would argue, look, this is the flat part of the curve. So a change in a lot, maybe a swing in 10% viscosity or moisture, we're processing in a viscosity that's lower. So, if I'm plus or minus 5% of 30,000 versus plus or minus of say 5,000, that's a, still plus or minus 5%, but down here, much lower range. But, I would stipulate that a 1/4 inch a second and a 1/2 inch a second here are most likely, depending on your part, reasonable injection speeds. So here, if I plot all this data, I would say maybe between 2 inches a second and a maximum of 12, that, okay, that's my range from the viscosity curve telling me I have a reasonable injection speed because I'm flatlining on the curve. But you're really relying on the shape of the curve and not really focusing heavily on the data. So if I took out these two injection speeds, now I'm plotting it from 12,000 relative viscosity versus 50,000 I had on the last slide. So we just said, somewhere between 2 and the 12 on the previous slide would look good. But now if I take out, some questionable speeds, then really I'm saying maybe that curve is dictating 6 to 12 inches a second. So I think you have to be careful. You can do this this curve and generate the information. There's nothing wrong with that. I struggle with people. You might come up with a range, but ultimately you've got to pick an injection speed. And I think there is more to picking that speed than using this curve. And that's also what, I want to go through here as well. And a lot of times if you generate this curve, the people that are you're learning will, absolutely press you to get these lower speeds because it makes the curve go exponential. And so you're really looking at the shape of the curve down here. And again, so if you see, if I take out that data, it kind of loses, it doesn't hold water there. So I'm going to plot this relative viscosity data on a log scale that I just showed you guys. And this is actually melt rheometer data for polypropylene I got online. So this is the data you would get from a melt rheometer. So let's plot those two together. So this relative viscosity in mole rheology, it's telling us viscosity is decreasing as flow rate increases, and we know that. But if we were to compare these two, that we're off by 1 times 10 to the fifth for the shear rate between these curves, and about 1 times 10 to the sixth. I'm sorry, for shear rate and viscosity 1 times 10 to the fifth. So if we really want to use this and say it's a real viscosity, we can't do that. If we could have a shift factor to some effect, that would help. So you see, when you compare this to viscosity data that's used in mold filling analysis and other simulations, that starts to break down as to the data you're generating, do the equations, and the shear rate, the values we're using for shear rate and viscosity. So limitations. Would I need to generate this viscosity curve relative for if I'm doing thin wall molding? We know we need to fill fast, but how fast is fast? It's not a proper term from a scientific point of view, or an engineer. We would talk volumetric flow rates. But what about PET preforms? I've molded these, and you typically inject, I believe, 8 to 12 grams per second based on the size of the preform, because we don't want to generate the shear heat to minimize the temperature so that we can cool the preforms and minimize the crystallinity. Then, molded many parts, automotive, cosmetics, and I can't just use one injection speed. I might be processing out some gate blush or just blush or flow lines throughout the length of the part. So to try to pick one injection speed in my career has not really worked out very well. I mean, it's possible. We can start there, try to keep it simple, but a lot of tooling and parts do not lend themselves to this approach by picking one speed, as we talked about. So let's talk about velocity capability. So you guys will, maybe benchmark your machine. I'm going to set the speed to say 10 inches a second, and this would be the expected velocity. So if I could accelerate instantaneously and fill the mold, I would be at 10 inches a second. Well, obviously nothing accelerates instantaneously. So as the injection speed set point increases, the distance from our perfect expected speed to fill the mold, if we could instantaneously accelerate, it's going to get greater. So let's take a little deeper dive and look at this. So I generated some data back in like 2007 for multiple injection speeds. So I did, the next slide, I have 1/4 inch to 1 inch a second. And the previous slide, I'm injecting up to about 12 inches a second. So I wanted to graph all this together. And one thing you should note is the injection responsiveness of the machine is fundamentally the same. The slope of this line, the ability to ramp up, is consistent. So obviously you can see the higher the injection speed, the less time we're going to be at that speed. And then if we calculate the average injection speed, obviously from the previous graph, you can see that as we fill faster, we're going to move further away from the perfect injection speed, meaning we're instantaneously accelerating. So with this velocity capability, the common method out there is basically calculating an average plastic flow rate through the injection. So we're really looking at distance traveled the average velocity during injection in the times its time. And I've put forward a second method that looks at percentage of fill time at that flow rate. So what we're ramping up, what am I really achieving? And this will force you to look at the curves. And I've seen a lot of people generate the velocity capability curves, the machine rheology curves, and not really look at the graphs and just plug in the data. And I think that's a downfall. There is a propensity to not feel comfortable with graphs, but if you're not really looking at the machine graphs, there is a lot you could be missing and generating some of this data and could be misleading. So let's look at some potentially misleading situations, being pressure limited, stability, responsiveness. So pressure limited, how do I know if I'm not pressure limited while I'm doing this velocity capability study or the machine relative viscosity? Yeah, we could check the peak pressure, make sure we're not exceeding that, but it's ideal to graph it and confirm that. With this curve here, we're graphing pressure here and injection speed, velocity, and over screw position here. So what we really have here is this is the injection speed that we are asking the machine to achieve. And this pressure here is 20,000. So we're telling the machine not to exceed 20,000. So you can see what happens is we start to inject, we hit the allowable pressure of 20,000 and our speed drops off. So we're no longer in closed loop control. We need a greater amount of pressure to continue the machine to inject at the program speed. So if I'm pressure limited, I might not catch that while I'm doing these two experiments. So looking at the graphs, verifying this is very important. Then also injection responsiveness. You wouldn't know how responsive your machine is if you didn't take a look at the graph. Now this machine is different responsiveness and ramping up to 10 inches a second and about 0.2 inches a second. So that's very good. I would take that on my 1995 Van Dorns that I started on, and I'd be happy if I got up to speed in maybe a half second. But if you're not looking at your curves, you could be missing out on how responsive is this machine. And don't forget, what we're generating this kind of data, we want to duplicate that plastic flow rate on another machine. So it's imperative we look at that and think about moving it, using it on multiple machines. I'll touch on that in a little bit. What if I had something like a decreasing oscillating waveform like this? You guys see I'm ramping up to injection very quickly, but I'm not, here's my set point, but I'm not stabilizing. If I were to do this, generating my viscosity curve or even the velocity capability, I'm calculating an average speed, I would never catch this. If I'm using the second method, which we'll get to, is where I'm looking at the percent of time that we're actually at speed, this would give us much different data showing us we're at speed for a certain time versus an average speed. So unless you would look at a curve like this, you wouldn't catch that. And it could be repeatable. Obviously, if it's still doing the same oscillating through the entire injection, we could actually get a repeatable, consistent fill time because the machine's consistently, quote, inconsistent. I guess you could say that. But here's an extreme example I've thought up is that what if the injection speed went, and this is a bit excessive, the area, it went over the programmed injection speed the same amount as it went under, and we actually transferred right here, barring that we didn't instantaneously accelerate, you would say your velocity is 99% capable, that your average speed was 99% of the set point. And, nothing could be further from the truth with this type of condition. So with that, let's get to some of the data I generated. So using the standard method of velocity capability. We do the expected fill time if the machine instantaneously accelerated at 10 inches a second over that distance traveled would give us a expected fill time of 185. But in this case, we really got an actual injection time of 0.21. So if we run it through the set of equations when we do this experiment, our average speed is 8.81. And we would say with method one that that's 88%, just move this over a decimal plate, that the average speed is 88% of the set point. And so typically anything over 80% when you do this experiment is considered a reasonable speed. And so let's take a look at that. So with this, it's saying every speed that we have the machine running at is capable and can be used. So with these curves here, that's really saying, let's take the red curve here with the 10 inches a second. I mean, yes, I ran this and it was consistently on top of each other and repeatable, but let's take a look at it. We have some ramp time to get there. Our speed is over traveling a bit, under traveling a bit, and finally stabilizes right here. So if I use the second method, in which all I'm really doing is looking at the fill time that is at that flow rate, you guys see I've got about 55%. So coming back over here, from about here to the end of fill, we're at speed 55%. Now, you guys will notice that this being a servo-driven machine, it's interpolating that you want to drop the speed on switchover. So I didn't include that. I negated that and looked at the time from here to here with method two. So that's what I've done for these two methods. And oops, let me go back. So if you take a look at this, I could argue that with the second method that we want at least the machine to be injecting at the programmed fill rate for 80% or better. And so what does that translate into? And so that's a linear speed of 6 inches a second on the machine. So if I take a step forward, what we're really saying here is the blue line, that we've ramped up, and from this point forward, we're at speed for 80% of the fill time. I was pretty strict when I picked these numbers. If I had to do it again, I probably would put a plus or minus 1-2% on that. But again, hopefully you see what I'm trying to do with an average injection speed versus a plastic flow rate in which we're at that speed. So if I take that 6 inches a second and say, okay, we're capable where 80% of our fill time is actually at our set point of 6 inches a second. Now, we have to think about this. We want to move our mold to another machine. So picking a viscosity or an injection speed off that viscosity curve, we've talked about the range and its shape being an issue. What about picking a speed that is going to be able to be duplicated on another machine? So hypothetically, 35, 30, and 25 millimeter screw. So I convert the linear injection speed to a volumetric flow rate, cross-sectional area times the velocity. And so we want to move our mold to another machine. We need to generate, if we use 6 inches a second with this 40 millimeter screw, we need to generate almost 12 cubic inches a second of plastic displacement. And you take a look at this, that would translate into, these are now the linear speeds on the 35, 30, and 25 millimeter. So as an extreme example, 6 inches a second to maintain almost 12 cubic inches a second is equivalent to injecting at almost 15.5 inches a second linear speed. I don't really know of any machine that's going to be able to do that. So this 6 inches a second might seem reasonable with the bigger screw, but then as you move to a smaller screw on a machine that you are going to potentially use in production, you want to debug this mold so that it can be run everywhere. And so what I did is I just took 6 inches a second is probably reasonable because I obviously don't have these machines and to run the data, but you could go to 8 here, maybe 7, 8 here. But you get the idea. What I'm trying to do in yellow is say that our machine has a velocity capability of these speeds being at the percent of the fill time being 80% or better versus just the average injection speed being 80% or better. So with that, I'm summarizing that so that you guys can see the different screw sizes would lend me to these injection speeds in terms of the 40 millimeter screw. So coming across here, 2 inches a second on the 40 millimeter screw would be equivalent to 5 with the 25 millimeter screw. So I'm suggesting to use these speeds. If you were going to debug the mold at 40 on a machine with 40 millimeter screw, you might consider only injecting up to 2 inches a second, which people would say to you, wow, you're really leaving a lot of speed on the table, but can I duplicate that on another machine? And that's an important question to ask. Maybe you can, maybe you can't. So another thing we can do to help determine where we should inject is a cavity imbalance study. And I've only seen this done when you pick one injection speed. And that's what I did here. I obviously picked an injection speed. And the goal here is to, I have an 8 cavity mold. And so we want to, I apologize, run these at different injection speeds. I've mainly seen it done, like I said, at just one injection speed, because if I pick the relative viscosity curve gives me a range, say on that first curve of 2 to 12 inches a second, we're going to pick something in between there. But this is taking it a step further. What would a range of those injection speeds really give me? If I were to pick 3 inches a second, what do I really achieve? And doing this cavity imbalance study shows that you could see it as I'm filling faster, that the cavities become more balanced. So if you guys look at this is cavity 1, 2, 3, 4, and onward to cavity 8. Here's the injection speeds I ran for the entire experiment. So you guys, I tried to target maybe 5% above and below the mean for the data. So, you guys can see here with a 1/4 inch a second, we're minus 25 for cavity 2, we're plus 9, 8 for cavity 8. So again, that justifies me taking that 1/4 inch a second, 1/2 inch a second injection speed off of doing that machine viscosity curve. So the next slide, trims this down to about 5%. So I regraph it such that we're at 4 to about 12 inches a second. And so, about 5 would be here, obviously 5 right here. So maybe this blue one is 10 inches a second. I'm out of that range a little bit. The green is really close to 5. But you can see what I've done is by filling faster, I was able to help balance the cavities. So, why is that? That could be due to shear rate, that we're getting a greater shear rate, more heat when we're filling faster, and that's helping us balance the cavities. So if we would just pick one injection speed off the machine rheology curve, we would not know this. We would not have this information that points us to a range of speeds that would give us a greater balance. And so I targeted plus or minus 5%. So with that, that's about on the next slide here. That's what the cavity imbalance is, about 4 to 8.5 inches a second, but on the 40 millimeter screw, because that's the machine I used. So this is some data that helps me, drives me, where should I inject? And just purely going on machine capability. And again, these numbers were done at a percent time at injection of 80% or better at the 40 millimeter screw and the 30 5, 30, and 25 are calculated. But the cavity imbalance shows me between 4 and 8.5. So if I were to debug this mold on the 40 millimeter screw, I know that between 4 and 8.5 inches a second, I've got a better balance. I know my machine is capable between obviously a quarter and then 6 inches a second. So this would lead me to surmise that maybe I want to inject between 4 and 6 inches a second for the process. I wouldn't have known that information had I not done these studies using multiple speeds. So what about my design of experiment? So now when I've seen it as commonplace when we pick that plastic flow rate off the machine viscosity curve, you are no longer using injection speed in your design of experiment because the shape of the curve has told you that this is the place to be, and you're going to live with that injection speed, and you're really leaving a lot on the table because remember we talked about shear rate, molecular orientation. If I fill faster, that changes my cooling rate. I get more shear heat. That's going to change my gate seal time. The cooling rate, the amount of crystallinity will in the part. So that crystallinity is going to affect shrinkage. So my part dimensions. So really in doing a design of experiment, you really want to capture all 4 primary plastic conditions and not negate the plastic flow rate because of how we picked it using the machine viscosity curve. So thinking about the DOE and moving forward now, this would give me a range that I would probably target based on the experiments that I did for my mold. And so I just thought I'd share with everyone. I've used quite a number of machines in the industry, and this Sodick is got a rather incredible control on injection speed. There's no reason why you would program a machine for injecting a part like this, but I was first introduced to the machine. I was kind of in awe of how fast the machine could inject. Right here we're filling at 0.114. So we just programmed, going from, to 7 inches a second, back down to 1, up to 7, up to 1, down to 1, and up to 7 over these distances. And this is quite incredible that, the machine is the time to go from here, if you guys think about it, is really a 1/10 of a second. Yet this machine was able to ramp up to to ramp and hit 7 inches a second, ramp back down, approach that 1 inch a second over that short distance, ramp back up, down, and back up. And that's pretty incredible. I have not seen that on any other machine throughout my career. The next graph, I just graphed this as a function of time. So you could see that this would be the 7 inches a second. This would be the 1 inch a second. So we are actually, reaching those speeds, in the fill time being 0.11 seconds here. So that's pretty impressive. So when we're talking about velocity capability on the machines, you are benchmarking machines and looking at them. This is something to note. We can do the different speeds as we talked about, but you could also program the machine to do something a little crazy like this. It's not a process you would run per se in mold in production, but this would certainly give you some feel for responsiveness of the machine up and down over different speeds, and perhaps try to quantify that as well. So I thought I'd share that with everybody. So with that, these articles I wrote for moving beyond this relative viscosity curve. We talked about another method for velocity capability, also using the cavity imbalance. So these are on Plastics Technology Online, or published up there. You can also see those articles on my website if you'd like. And I'd also just point out that, I do a lot of injection molding training publicly and then customize on site. And so doing a class at Sodick in LA area, May 12th through the 14th. So with that, that's what I had for the presentation. And I'll say a few things that, I've taught this quite a number of times, and I'm really not telling anyone to not do the machine viscosity curve. I'm not telling anyone not to do the velocity capability study method one that has been, taught and done for years. What I'm suggesting is to, perhaps you can get a better idea of what your machine is capable of, what machines are repeatable on different machine, from moving molds from one machine to another. I mean, that's the whole purpose of scientific molding. The purpose of doing these experiments is for scientific molding. So I'm not telling anyone not to do this. I'm just suggesting to be aware of the data you're capturing and what does it truly represent, and how are you interpreting it, and how are you using it to set your process in production. So with that, I will turn it back over to my friends at Sodick, and I believe we'll open it up to questions.
Yeah, thanks, Umberto. That was very interesting. We're
welcome.
going to have some questions coming in here. And if you have any questions that come up as we're going through this, definitely post those in the Q&A portion of this webinar. I have a couple that have already come in, so I'll go ahead and get started here, Umberto. This first one says, thank you for showing method 2, which shows the percent fill time at the desired plastic flow rate. How did you calculate these percentages, or were they visually estimated based on the plot of measured and set injection velocities?
Yeah, I actually brought up the curves themselves, and I, basically just plot the injection curve and went across with the cursor and looked for the speed to stabilize, and I could come through and capture that time. So, perhaps I'll just bounce back a few slides here. So basically I would plot this, well, let's just do this, say this one. Obviously we ramped up to speed perfectly, but let's say the 10 inches a second, I would come across this curve and just look for the speed to stabilize at 10. And that's, subtract that time right there minus the fill time, and what is that percentage, and that would be your percent at the programmed plastic flow rate.
Okay, thank you for that. Let's get a couple more in here. Here's another one. Which method of velocity capability would you consider using during future machine benchmarking?
As I said, I'm not opposed to using both. I think it's still good data to capture. I just really adamant about, when I teach and go in and do consulting and to get people to really look at these curves, I find a lot of people on the floor are intimidated by them. But just doing the studies and really looking at the data, the curves, I think goes a long way for you when you're capturing the data to go, is this reasonable injection rates or speeds? Am I ramping up to something reasonable, or am I getting that chatter like I saw on like I showed on a couple other curves theoretically? So I think you can use both. I just would keep in mind what each of them are suggesting to you.
Okay, thank you. Let's go to a couple more here. I got a good one. Do you support on-site process development?
Do I support?
Yeah, like do you
I
provide on-site process development?
Oh, absolutely. Probably 50% of Orbital's business is doing injection molding training publicly, and also on-site customized training. And training courses, but I do a lot of processing and troubleshooting in the industry. When people are having issues making parts or what have you. Is it the mold, the machine, the material, the process? It's absolutely one of my favorite things to do, to really get out on the floor and run people's equipment. So absolutely, we do that.
I know that.
Good, good. Okay, let me get to one here. This is a little bit lengthy, but I'll read it out to you. Utilizing cavity balance is informative for establishing fill rate. I think testing a low, medium, and high is a good preliminary test. Do you think the DOE is the final word on whether or not the fill rate is appropriate? Then you're actually including dimensional and attribute results to drive the decision. Yeah, thanks so much.
Yeah, I think that's fair. Yeah, a low, medium, and high would be very reasonable. And that's one of the things when you mentioned dimensions, and we never talked about that in this whole presentation, or when I do a lot of scientific injection molding training, we're focusing on what the machine can do, this window, but we never really looked at the quality of the part. We never looked at the dimensions, hence the cosmetic comment I made previously. So I like your question, and I always try to point that out after teaching, that we haven't really focused on the root, not the root, but what we're shipping our customer, good parts, dimensions. So I would absolutely look at dimensions, and I would have the dimensions drive my DOE more than anything else. I have found that dimensions is king. Obviously, we want to ship parts to spec, and so I tend to focus on that very heavily when I'm doing design of experiments, and also troubleshooting and things like that.
Gotcha. Thank you for that. Here's another one. It starts off with, "Thank you, Umberto. You're a great teacher." So I'm sure you like to hear that.
$50 in the mail.
How do you feel pressure sensor linearity, hysteresis, repeatability from press to press affects the result? If one sees plus or minus 1% full scale output variation from one pressure sensor to another, what's the best way to know what's truly happening in the press with regard to pressure?
So are we talking, does it specify in cavity mold sensors, or are we talking the pressure, plastic pressure that the machine is using?
I'm gonna guess that it's in cavity.
Okay, could you read the question again? I apologize. That's pretty lengthy. Let me think about in cavity pressure while read that again.
How do you feel pressure sensor linearity, hysteresis, repeatability from press to press affects the result? If one sees plus or minus 1% FSO variation from one pressure sensor to another, what's the best way to know what's truly happening in the press with regard to pressure?
That's a very good question. I don't know how to truly ascertain what is the true pressure. We're getting different readings. I'm assuming it's the same mold in two different machines. So I think it would be kind of hard to ascertain which one is absolutely correct, or perhaps you're referring to two different molds being run. I think 1% is, I don't know if that's livable for you guys. Perhaps you're doing medical molding and your tolerances are so tight that if your peak pressure on a cavity pressure curve, or whatever pressure you might be monitoring, I would hope that 1% would not skew you to make bad parts. But I don't think I could truly answer the question with what's in front of me.
Okay, yeah, he clarified that he was referring to hydraulic pressure or plastic pressure in the cavity, either one. So
we're inside the cavity.
yeah.
If I'm seeing 1% difference of pressure, I could easily argue that that's just slight change in, lot to lot number. Dryness has a huge effect on the viscosity of the material. You're going to see that kind of variation in molding day to day. I'm assuming this is where we're going. And it would be certainly good to know that percent difference. And am I really making good parts? I'm trying to feel my way through this question. But ultimately, if I'm seeing this 1% difference, maybe I can't quantify it, but am I making good parts? And I would measure dimensions. And can I live with this 1% you're talking about and still make good parts for my customer? Perhaps
Gotcha.
we could talk offline, and I'd be happy to talk more about that if I had a 100% grasp on the question.
No, I got you, and I can give you some of this Q&A data
You guys,
afterwards, and we can reach out.
absolutely. Call and
Great.
harass everybody else does.
How about this one? What do you think is causing the cavity imbalance observed during your experiment?
Yeah, that's a great question. It's got to be shear rate related. If I had to do this over again, I would like to gone back and like I said, I got this in 2007. I did this, so I'd like to go back and get the actual gate diameters. Is that really affecting it more than maybe the shear rate of the different injection speeds? I think you guys are probably familiar with an 8-cavity mold where the 4 inside cavities fill faster than the 4 outside, and hence the melt flipper that John Beaumont has invented to help balance the temperature flipping the melt. I really can't say, and I wish I had the money to go back and actually potentially even change the runner design instead of the sharp that we have. Maybe if I rounded it out, would that show as much imbalance? So I think that's a great question, and I'm not 100% sure, but I'd have to say it's shear heat related.
Thank you, thank you. A couple more here. Does injection response get better with newer machines? If so, what is the factor?
Oh, I don't know the factor, but certainly I really can't believe I've been doing this for 30 years. But when I started off on 1995 Van Doren HTs, if I could ramp up to my injection speed and it's kind of what speed, but maybe in a half second, I was very happy. But with the advent of the servo hydraulic and servo driven all electric machines, it's just incredible the rate of speeds that these machines are capable. I never thought I'd see anything like this, but I think obviously I've run servo hydraulic, I've run servo driven direct drive as Sodick, but I think it's going to be specific to the machine. You can have a servo driven machine A and B, but which one really performs the best? And I would look at those velocity curves and plot those same, convert to volumetric flow rate and run machine A and machine B with the same mold if possible at the same speeds, and what kind of responsiveness am I getting? I think it's to be machine driven. And also one thing I'd like to point out, there are some machines out there. If you guys remember the graph I showed with the different responsiveness, I was actually able to program the machine to do that. Now, in my day, you would have to tune the valve to have a hydraulic valve be more or less responsive. But there's several machines out there that let you change the actual responsiveness of the machine during start of injection. So I hope I answered your question, but definitely driven by different machine manufacturers. I would say is a big, one of the biggest factors.
Okay, thank you for that, Umberto. I think I got one more, maybe a couple more will come in, but You mentioned velocity capabilities greater than 80% for both methods. What do you propose for vintage or older machines that lack the responsiveness and stability of the all-electric machine data you presented?
I get that question, and I would throw out 50%. I gave you the example with the Van Doren when I first started, and I even had some vintage green monsters, we called them back in the day. If I would throw out maybe 50-60%. If I could just get it up to speed for that period of time, I was pretty happy back in the day.
Okay, well, great, awesome. I appreciate it, Umberto. I don't know, Kohei, do you have anything you wanted to add on as well?
I would just one thing I'd like to add, and I wanted to mention this, is that I do write articles for Plastics Technology magazine, and I consider it an honor to do that. But if anyone has some ideas of what they might want to see in an article, please email me or make a suggestion, because I kind of struggle as what to write, because a lot of this has already been written about, and I feel that it's redundant. But if someone has some ideas of maybe what they would like to see, I'd love to hear it. Maybe I could write on it. So just keep that in mind.
Thank you. Thank you.
Great, yeah, thanks, Umberto. Yeah, Kohei, did you have anything?
No, just thanking Umberto to come back again, and see you soon.
I'd be
Yeah,
happy.
Umberto, I'll ditto that. Thanks, Umberto, as always. You've been a great resource to our customers for sure throughout the years. And we really value our relationship with you. Thank you.
Appreciate it, Lynn, and I'll send the $250 in the mail for that. Appreciate it.
And please
Sure.
see us at the MDM West and the PT Expo. And
Yes, absolutely. We'll be at both shows, and we'll have booths there, and some of our partners will also be joining us in those booths. So we look forward to seeing you guys there, and we thank everyone who joined us today. We appreciate you guys supporting this webinar series, and we look forward to seeing you at the next one. So stay tuned.
thank you.
Thank you, everyone.
Thanks, everybody. Thanks for joining.
Have a good day.
Bye.
Bye-bye.